Hello everyone. Today, let's discuss the problem fork from the 2023 British Informatics Olympiad final. This is part of a video series, so I'll link the playlist in the description down below, where you can check out the other problems from this Olympiad. But this is an exciting day because we have a guest joining us today in today's video. So Boris, who's a fellow contestant, he's another contestant who made it to the final and did pretty well. He solved this problem as well, so we will both be sharing our solutions to this problem in today's video, so it should be fun. So I'll talk you through the problem statement initially and some initial observations. I'll set the scene and then we'll dive into the solution. So both of us will share our code as well in the video. So it should be fun. Let's dive right into it. So first of all, the problem. What's the problem? So I'll put the link to the problem in the description so you can check it out. You can read this if you want to, but I will take you through the problem on a whiteboard. Okay. So in this problem, we have some spies sitting on a long table which has two sides, essentially two rows. So this thing here represents a table. I'll explain what the numbers mean in a second, but essentially each of the numbers represent a seat on the table. So there are two rows, and so the table is 2 by n. So you have a 2 by n table, and the numbers represent pieces of cutlery. So there are m different pieces of cutlery, n types of cutlery, and so each spy is holding one of those types, and so the numbers in here will be from 1 to m. So each of these numbers is from 1 to m. Let's say, well, in this case, in this example, n is equal to 5 because it's a 2 by 5 table, and let's say m is 4. So we have 4 types of cutlery. Nobody's holding cutlery of type 1. A bunch of spies are holding cutlery of type 2, as you can see, and two are holding type 3, and 1 is holding type 4 over here. So that's what it looks like. And so these pieces of cutlery aren't fixed, so spies can change what cutlery they're holding. But one change causes a sort of chain reaction. So let's say this guy changed his cutlery. His neighbors might also change their type of cutlery, depending on some condition. So first of all, what does neighbors mean? Neighbors mean somebody who's sitting directly next to you, so to your left or to your right, or somebody who's sitting opposite you, so down or up. So this guy has 3 neighbors, this spy. Every spy has 3 neighbors, essentially, except for the spies on the ends, which have only 2, like this. So this spy has 3 neighbors. Let's say this spy changed its cutlery type to 1, from 2 to 1. What would happen? So if you change your cutlery type, every one of your neighbors that had the same type of cutlery as you before you changed will also follow your change. So since this was a 2, since this spy was holding cutlery of type 2, this neighbor over here is also holding cutlery of type 2, so they will follow that change. And so will this neighbor. This neighbor is holding cutlery of type 3, so they won't follow that change. This won't change. But this, as I mentioned, turns into a chain reaction. So now this 2 will also change because it is a neighbor of another value that just changed. So this 2 will also change to a 1. So if you think about it, this is essentially what the table will look like after the change. So these values will remain unchanged, but all these 2's will change to 1's. Because this one affected this one affected that one, and this one also affected this one. So that's how the changes work. Then let's say the same value changed to a 3, from a 1 to a 3. Well, then all 4 of those 1's would again change to 3's. So all 4 of these 1's would change to 3's. So these 4 would now become 3's for the same reason, in exactly the same way. But now if this same value changed back to a 1, these 3's would follow as well, because they will be affected by the chain reaction. So now you'd have those 3's following as well. So that's how this works. So we've drawn sort of 3 changes, 3 steps here. This isn't actually what happens in the problem. So in the problem, this value can't just decide to change. So this 2 that we mentioned can't decide to change. In the actual problem, only the top left value can change on its own accord. So every other value responds to chain reactions. Every other SPI responds to chain reactions, but doesn't just decide to change itself. So that's why the top left value is called the trend setter, because it sets the trend and then every other SPI sort of follows. So let's take a look at an example from the problem statement. So over here, let's look at, there's a lot going on in this diagram, so I'll just zoom into the relevant part. So this is a 4x2 table, so n is 4 in this case. And the trend setter initially has value 1. And so only the trend setter changes. So at the top I've written what changes the trend setter makes. So the trend setter starts at 1, then it changes to 2, then it changes back to 1, then 2, then 1, and then 3. So let's see how this affects our table layout. So when the trend setter changes from a 1 to a 2, nobody follows the trend setter because none of its neighbors had the same value as it had. So none of its neighbors had a 1, sorry. But now this neighbor also has a 2. So the trend setter has the same value as this neighbor. So that means when this trend setter changes back to a 1, this neighbor will follow. So these will both change to 1's. But now, again, this neighbor, this value now is sort of in the same component as the trend setter, in that you can start from the trend setter, keep moving to neighbors with the same value, and reach this SPI. So that means that if the trend setter changes, this SPI will follow because it's in the same component. Let's call that a component. So when this trend setter changes back to a 2, both of these 1's will now follow. So all 3 of these will change to 2's. Now again, this 2 is now inside the trend setter's component, because if the trend setter changes back to a 1 now, this 2 will be affected because the trend setter will change. That means this value will change. That means this value will change. That means this value will change. So this chain reaction will affect this node, this SPI. And so when the trend setter changes back to a 1, all 4 of these 2's will change to a 1. And now this 1 on the end joins the trend setter component. And so when the trend setter changes to a 3, all 5 of these 1's change to 3's. And so in this case, at the end, every value is a 3. That doesn't have to be the case. So at the end, in this case, every value is in the trend setter component. So the question the problem is asking is, by the end of all these changes, so you're given the initial layout of the table, and you're given what changes the trend setter makes, and you want to know by the end of all these changes, how many spies on the table will be holding the same type of cutlery as the trend setter. So in this case, it's 8 because they're all holding the same type of cutlery as the trend setter. So the trend setter has 3, and every value is a 3. So in this case, the answer is 8. Let's take a look at a second example. This is, I believe, the example, the sample input here. So in this case, these are the trend setter's values. So this is what the trend setter, these are the trends that the trend setter sets. So how does that affect this board this time? So in this case, the table is 6 by 2. So we have 6 people sitting on each side of the table. So the trend setter starts off with a 4, and actually this very much resembles the previous example because, if you can see, the first 4 by 2 section of this table is the same as it was here, and the changes are essentially the same as well. So most of this is actually the same. So the trend setter changes to a 2, this 2 joins its component, then it changes back to a 1, both of these change back to 1s, then this 1 joins the component, and so on. So changes back to a 2, changes back to a 1, changes back to a 3, and so we end up with the same end case as in the left side example, but these 4s sort of form a barrier because the trend setter never changes to a 4. Well, it was a 4 initially, but these 4s weren't in the same component. And so at the end, we have these 8 3s, as we did in the left side. Then we have 2 more 4s, and then 2 more 3s. So we can see here that you don't actually have to be in the component of the trend setter to have the same value at the end. These 3s do have the same value at the end, but they're not in the same component. So in this case, the answer is 10, even though the size of the trend setter component at the end is 8. So the answer at the end will be the size of the trend setter component. So how many values are in the trend setter component at the end, but also plus how many values aren't in the trend setter component at the end, but start off with the same value that the trend setter ends on. So if we take the last value that the trend setter takes, the last type of cutlery, if there are any spies that start off with that type of cutlery and never join the trend setter component, well, at the end they'll still have the same type of cutlery. So if we can somehow work out by the end of all of these changes that the trend setter makes, who is in the trend setter component and who is not, we can relatively easily find the answer, because the answer will be how many people are in the trend setter component plus how many of the rest already initially had the same value that we're looking for. So already had the trend setter's final value as their start value. So that is essentially the question. That means that what remains is how many people by the end will be in the trend setter's component. So how do we find how many people will be in the trend setter component by the end? So we'll do this by sort of simulation. So we have to somehow simulate these changes, but we have to do it fast enough, because if you check the limits in this problem, n, which is the number of seats on each side, is up to 2 to the 20, so that's around 1 million. And so is the number of changes that the trend setter makes. That's also up to around 1 million. So with those constraints in mind, we have to work out who will be in the trendsetters component, which spies will be in the trendsetters component by the end of all these changes. So that's the point we've reached. So I'm excited to welcome Boris. Thanks for joining us, Boris.
Hello, thank you. I'm proud to be in the presence of a grandmaster. So, yeah, thanks for having me.
Nice to see you again after the final.
Yeah.
And so yeah, thanks for joining us. Boris will be taking us through his solution, which is quite neat. So where we got up to, Boris, is essentially transforming the problem into having to work out which values by the end of all of these trendsetter changes will be in the trendsetters component here, which is what I've drawn at the bottom. So we have, and I've shown them the constraints as well. So we want to do that relatively quickly.
Okay.
Yeah.
So
take it away.
All right, sure. So the way this algorithm is going to work is we're gonna first have a matrix that's just the same size as the one we have right now. That's just got ones and zeros. That's just going to say 1 if the person at that index has a piece of cutlery that's in the trendsetters component, and 0 if they are not in the trendsetters component. So that's going to be designated by red on the whiteboard. And we're also going to have a set that's going to be ordered by the piece of cutlery that the person's holding. And I'm going to write that in blue. And this represents the border of the component. So basically, the values that could be influenced by a change in the trendsetter's cutlery. So at the start, we're just going to have the trendsetter themselves in the component, and the ones directly adjacent to them will be in the border set.
Yeah, so we've got the red set, which is in the component, and the border set, which is everything that's neighboring.
Yeah, exactly. And on each time the trendsetters component changes, we're going to have changes in both sets. So, whoops, sorry. How this works is we're going to, we know that the important people are just the ones that are bordering the trendsetters component. So we don't need to, it'd be very inefficient to kind of just go through all the numbers and do something a bit strange like that. But what we can do is we can just check through the trendsetters component which of these numbers have a value that's equal to the cutlery we're changing to. And if the cutlery that we're changing to is the value that they have in the component, we can then put that person into the trendsetters set. And since we have an ordered set, we can use binary search to find the range of people who have that correct cutlery in the set. So when the cutlery changes to 2, we're going to have these 2 in the set, as you've shown on the left, because 2 is the cutlery changing to. 2 is now part of the trendsetters component. And then anything that's now bordering the set will be added to the border. And we basically just repeat this over and over again. But one important thing to mention is we can't just check the values in the border set. Once we find that some value in the border set has the correct cutlery, we then need to start a DFS from that place in the matrix, and we need to see if there are any more people who are also adjacent because now that we've added this person into the trend setters set, we then need to check the people bordering them, whether they also have the same piece of cutlery. And as soon as we reach one that doesn't, they'll be added to the border set, and that forms the basis of the next iteration.
Yeah, so if this was also a 2, what you're saying is that from this 2, we'd have to do a DFS that takes all 3 of these 2s into the trend setter set.
Yes, exactly. Yes. So, yeah, exactly. And then what it would look like is that this would be red, this would be red, this would be red. And we would get to the end where we've DFS'd to a number. These 2 that are not 2, they would be added into the border set. So that's how that would work. Now, I guess we can follow it through one more time, maybe, and then we can look at what happens at the end. So, okay, now we are changing. Now we're changing to a 1. So let's get rid of these. So now just the same thing happens again. That's a 2. That's a 2. That's a 1. And this number will still stay in the border. We're not going to get rid of it or anything. But now this 2 here is now going to be in our border. And that's pretty much how it works. And then you can kind of imagine how that would develop. It's not too challenging. So the first one here is when we were changing to 2, and now we've changed to a 1. So we keep the values that were already in the trend setters component, and then we added the 1 that was in the border into our component, and it's now 3 and 2. Oh yeah. I guess we could it'd be probably best to write these as a 1 now. It's worth mentioning that the numbers that are written as all 1s here, I'm not actually going to change them to 1s in the code because that would take too long. This is just an illustration. In reality, these aren't going to be changing. They're just going to be represented in the visited matrix as a 1, as to show that they're part of the trend setters component. But yeah, does that make sense?
Yeah, so the numbers changing here are just for us to visualize it.
Yeah, exactly. So once we get to the end, we need to count how many numbers are part of the group that have the same end number as the trend setter. So the way we check that is we just go through every position in the matrix, and we check either A, it's in the trend setters component already, and that will be represented as a 1 in our matrix. That just keeps track of which ones are in our component. And if it's not in our component, we can't fully discard it. We also need to check whether it's has the same number as what the trend setter ended on, but it's not necessarily in the set. So these 3s that you've labeled here on your original one.
Yeah.
So the ones in the purple box on the left, they'll be counted as those that are marked as in the set. The ones on the right, those will be the ones that aren't in the set, but do have the correct cutlery. So I guess that's pretty much it for the explanation. I guess we can get onto the code now.
Yeah, 1 second before you go. So the main neat idea that you had here was when I was in the contest before I moved into whatever crazy solution I cooked up. The idea that I didn't see actually, and it's a pretty neat idea, is that obviously these blue values are in the border set, which are the borders to the current component of the trend setter. And so if you were to traverse all of the borders, so all of the blue values every time, that would obviously be too slow, because you could have the trend setter changing to types of cutlery that nobody has very frequently, and so this border could be huge. This border set, for example, if you had the whole top row in the trend setter set and the whole bottom row would be the border set, so checking that every time would be really slow. And so what the good idea about this solution is that if you store those in a set, you can actually just binary search to the ones with the same value that you're changing to, which is really cool.
Yeah, exactly. So as I was explaining earlier, we're going to have one vector that keeps all the cutlery in the table, one vector that keeps track of which people are in the trans-status component, and an ordered set that keeps track of the people on the border of the component. And what we're doing is instead of storing it as a two-dimensional vector, we're storing it as a one-dimensional vector. So we're basically just compressing everything down into a single row, because it's just easier to represent positions as a single number rather than two. So what we're doing is we're just taking the first row and putting it in the first 0 to n-1 indices, and then we're taking the second row and we're putting it into the next, the remaining n to n-1 indices. So that's how we're going to represent our positions. So first, when we start the program, we're just going to take in our inputs, and we're going to call this visit function on the top left corner of the table, so the trans-setter, and we're going to pass in the index and the value. So what this visit function does is it handles whenever there's a change in the cutlery that we're using. So we are going to start a DFS from index A, and we're going to look at all the adjacent people who have the same type of cutlery that we're changing to. So what we do is we have a stack that will just be our medium for our DFS that just contains the starting index to begin with. And on each iteration of the DFS, we first check, is this value already in the component? If it is, then we don't need to examine the neighbors and revisit nodes we've already visited, so we can just continue. Then we check that if the value of the cutlery that this person is holding is equal to the type that the trans-setter is changing to, we can then get rid of it from the border if it's there and add it into the component, the trans-setter's component. Then what we do is we then need to add to our stack the positions in the table that are adjacent to the one we just added to the component, because now our border has expanded and we now have these other indices that are in the border. So what we need to do is we need to check that the index isn't on the far right of the table. So what we do is there's two options. Either on the first row, it's on the far right of the table, it would be index n-1, or on the second row of the table, and it would be at the far row of the table, in which case, when you take the modulo, it would also be n-1. So we basically just check that we're not on the far right of the table. This one, we're just checking that we're not on the far left of the table using a similar idea, just so that we don't accidentally visit an index that is not actually adjacent to the one we're on or is outside of the table. And then we can also visit either the above or below, just by doing this. It's just a sleek way of doing this. So we assume we're going down, and then if we're past 2n, we then wrap around, so it's like we're going up. And if the value that we're looking at is not equal to the cutlery that we're changing to, we can then add it to the border set, and it's going to be used for the next iteration. So that's pretty much how the DFS bit works. So once we have this function is going to help us keep track of, firstly, what numbers are in the trans-status component, secondly, what numbers are in the border. So this function will basically help us manage the change. Then what we do is we go through all of the trans-setters changes, and each time there's a change, we then go through our ordered set and we binary search to find the range of values whose cutlery type is equal to the one we're changing to. So the way the set is ordered is that we have a pair of integers. The first value in the pair, which is what the set's going to be ordered by primarily, is going to be the cutlery type. And the second value will just be the index, so we can refer to it. So when we use lower bound, we can then find where the first index is that has this type. And then we can basically just keep iterating until we either reach the end or we're no longer of the same type. So I'm basically just going to add everything into a vector. Because our set's going to be changed by our visit function, I'm going to add it all into a vector beforehand, and then I'm going to visit all of them. So once we add them all to the vector, all the indices which have the correct cutlery, we're just going to go through all of them, and if they're not already in the transcendence component, we're going to start our DFS from that index and expand our component and our border set. And the reason I do this, you might think, okay, but if we're in the border set, surely we're not in the component. Well, when we visit things, we might actually add something to the component that wasn't a border set before. So we're just checking that it hasn't been added already. And once we finish going through all the cutlery types, we then go through all the indices in the table. And if either they're in the transcendence component or the piece of cutlery that they have is equal to the final piece of cutlery that we're changing to, then we can add it to the answer and we can print it out. And that's pretty much how the code works. So does that make sense?
Cool. Yeah, it does.
Okay.
Not very long implementation or anything. Pretty neat. Yeah. Nice that you have DFS without recursion. That's interesting. Was that because of the British Informatics Olympiad sort of servers? Because I know in last year's final, the stack size wasn't big enough for a recursive solution that I had, so I had to change it. So is that the same for you, or did you just implement it like that?
That's a good question, actually. I don't know. I just wanted to use a stack. I think you're right though, because this stack, you could be DFSing like up to or like over 1 million things in the worst case, right? So I guess you kind of don't want to be like repeating these parameters every single time on the call stack. So yeah, that is the motivation to do it. I did write this code a long time ago, so I can't tell you if that is why or if I was just in a stacky mood. Yeah, that's there's no preference there apart from maybe memory usage.
Yeah, it is something to note that I think most online competitions and things like that don't have a small stack size limit for recursive functions, but the bio one does. So
yeah, I mean there were a few technical issues, weren't there? I think someone's computer managed to shut down and they lost like 15 minutes of work, but hey, well, it happens, you know.
Yeah, I think the problems were really nice though, in my opinion.
Yeah, I agree. I'll be happy to watch your video later to see the solutions to the ones I missed. So I'll be excited to hear you explain those.
So just one thing to note is that Boris's program is pretty fast, I expect. So one thing I noticed is that you can sacrifice some time. It'll need some more binary searches. It'll have the same time complexity, but it'll be slightly slower probably to change how this is an alternative approach. So instead of let's say we have this example, so the red is obviously the component and the blue is the border set. So if you take a look at this 2, instead of DFSing from the 2, you could so say we're changing from 1 to a 2, we could add the 2 to the component and then add these 2's, its neighboring values, to the border set. So make this 2 red, make those 2's blue, and then repeat the same thing. So we'd have to search again. We'd have to do another lower bound in the border set every time. So that would be like a while loop. So you'd save having to do the DFS, but you would have an extra while loop in there to do this. So then you add this 2 to the set, you'd make this 2 blue, then you'd say add this 2, they'd make the 4 blue, and then finally you'd add this 2. Oh, and there's one more too. So essentially, by the end, you'd end up with the thing I've drawn down here. So you, instead of DFSing, you could also do the stack, not the stack, just binary search every time in the set as well. But
yeah,
of course, it doesn't matter.
I mean, as long as you have the right time complexity, usually the performance constraints aren't too bad. I mean, I know in this one, you could have gotten away with doing that for sure. It's just down to whichever you find easier to implement, probably just do that. And so you can save time in the contest and move on to the other problems. Yeah,
I mean, if you're feeling stacky, you can always...
Exactly. I love stacks. But yeah.
Yeah, so very nice solution. Cool.
Thank you. It was the only one I got, so I'm very proud of it.
Well, it was more than many people, so
yeah,
nice.
That's true. But yeah, thanks for having me.
Yeah, cool. And coming up, we have in around a month, right? Less than a month, the Western
like 3 weeks,
European,
I think.
the Western European Informatics Olympiad, which is the first ever of that kind. So looking forward to that. Traveling to the Netherlands.
You aiming for a gold medal?
Hopefully, we'll see. We'll see.
That's good.
Should be interesting.
I'm gonna aim for a bronze personally. I'll try my best, but yeah, it'll be nice to see you in person again in a couple of weeks. But good luck. Good. I know you're doing your A-levels soon. Good luck with those as well.
Thanks.
But yeah, thanks for having me.
Hope your exams went well as well.
Yeah. Okay.
All right. Great to see you, and maybe we'll meet again in a future video.
Yeah, maybe. All right.
Do you have a YouTube channel, by the way, that we can link?
I do. I'll send you the link on Discord afterwards. You can put it in the description.
Boris's YouTube channel in the description.
By the way,
check it out.
By the way, a shameless plug. I actually made a video where I explain the round 1 solutions. So here we have the round 2 solutions from the man himself who knows everything. And then you have me, slightly less capable, but I've got a good video detailing the explanations to the round 1 solutions on my channel, so you can check that out as well. So,
that'll be in the description as well. So definitely take a look at that.
All right, cool. Bye.
So I'm now going to talk you through my solution to this problem. It's the technique I used is not necessary. It's not required in this problem, as we already mentioned. The solution we already discussed is the intended solution, but this is still a useful technique in my opinion, so I'm going to talk you through it nonetheless because it can be useful in other scenarios as well. So what are we trying to do? Let's remind ourselves. So we've transformed the problem into having to work out how by the end of all the trendsetter changes, so these changes up here, which nodes, which spies will be in the trendsetters component. So we have to work that out. And then again, as we've already discussed, if we know that, then we'll take the number of those and add to that the number of values that were not in the trendsetters component at the end, but started off having the same value as the trendsetter's final value, so they're still equal. So in this example, the answer is 10, which is 8 plus 2. 8 in the trendsetters component, and 2 in that second category. So again, how do we find this component? Who will be in the trendsetters component by the end of all these changes? So my solution was different to that because I didn't spot this idea on the border, on binary searching on the border set. So instead I did something else. So here I've just copied over the starting layout for that table, and these are the changes that the trendsetter makes. So I've indexed them. So I've indexed 1 through 5 because the trendsetter changes 5 times, and I've indexed
index 0 as the trend setter's initial value. And so let's say these black indices at the top sort of represent time passing, because at time 0 the trend setter's value is 4, at time 1 the trend setter's value is 2, and so on. So that's how we'll discuss it. And so the main idea that I used is I applied Dijkstra's algorithm to this problem. Now you may be saying, what? How? There is no graph in this problem. So you can make a graph in the problem. Well, or you may be saying, oh right, cool, I already knew that. In which case, I mean, fair enough, you don't need to watch this video. But if you don't know how that's done, then you can turn this into a graph so we'll make the spies into nodes, and we'll connect neighboring spies by edges, like so. So essentially it is a graph where every pair of neighbors is connected by an edge, so that it looks like this. So the entire top row will be connected, the bottom row will be connected in chains, and then opposite nodes will be connected as well. So that's the graph. So we can run Dijkstra's algorithm on this. So we have to get something straight, because that's slightly confusing if you just say it. Because, I mean, Dijkstra's needs a concept of distance, a concept of reachability, right? So what do these edges mean? Why are we moving between nodes here? So essentially we want our algorithm, our Dijkstra's algorithm, to tell us which values are in the trend setter's component at the end of all of this. So why don't we say that? Why don't we define the distance from the trend setter to a node, which is what we need in Dijkstra's algorithm, right? That's the definition. So in Dijkstra's algorithm, we're finding the distance from the source to every other node. So in this case, the distance from the trend setter to any other node is the time, I guess. So is the time after which the node is in the trend setter's component. So we need that sort of concept. I mean, Dijkstra's algorithm, yeah, distance/time, because Dijkstra's algorithm finds the shortest distance, but that's also usually equivalent to problems where you spend time to traverse each edge. So the distance to a node will be defined like this, essentially. So in this case, in this example, the distance from the trend setter to itself is 0, obviously, because it's already in its own component. The distance to this node will be 1, because after one move, after one trend setter change, the trend setter becomes a 2, and so it's in the component of this 2. So if you think about distance in terms of these early diagrams we were going through, the red is the trend setter's component, when we were discussing it over here, and so the distance to a node is essentially how long it takes for that node to become red. So for this value, it would be 1, 2, 3. 1, 2, 3, 4. So for this one, it's 4. So for this one, the distance to it is 4, because on the 4th trend setter change, it becomes part of the trend setter's component. So that's what distance means. Well, then why do these edges make sense? That's because, well, if you want one node, one SPI, to become part of the trend setter component, it has to happen through these edges. So, for example, for this node, this 2, to become red, to join the trend setter component, what happens in the actual example is that this 1 becomes part of the trend setter component. So all of the trend setter component grows to this size, containing this 1. And then the next time the trend setter changes to a value of 2, which is here, that's when this 2 joins the component. But in a way, this edge facilitates that. So if one of your neighbors is in the trend setter component, then you can also join the trend setter component the next time that the trend setter changes to your value. So without any of your neighbors being in the component, you can't join the component. Well, you might ask, what if multiple nodes join the trend setter component in one move? Let's say you have the trend setter up here with a value 1, and then a bunch of 2s next to it, and then we don't care about the bottom row. And let's say this 1 changes to a 2, and all of these 2s join. Well, we can still use this same definition of edges, because the 1 leads to this 2 joining the component, because when the 1 becomes a 2, this 2 is now in the component, and then at the same time, this 2 joins because of the previous 2, and this 2 joins because of the previous 2. So these edges facilitate movement between nodes in a way. So when you're moving between 2 nodes, you're actually saying that the initial node was in the trend setter component, and that puts the next node in the component as well. So what's the actual weight of an edge then? Because in Dijkstra's, we want weights of edges. We want edges with weights. So the weight of an edge actually isn't fixed. Why? Well, let's take an edge. Let's take this edge. Let's take this edge between the 2 and the 1. So it depends on which way you're traversing the edge, right? Because if you're traversing it from left to right in this case, so from the 2 to the 1, that means that the 2 is already in the trend setter component and the 1 has to join the component. And that will happen at a specific time, right? The next time that you see a 1 in this trend setter change list. But if you're traversing it right to left, then it's the next time you see a 2. So it depends on which way you're traversing it. But it also depends on how much time has already gone by. So it depends on 2 things. So weight of an edge depends on direction that you're traversing the edge, and also the time of arrival. So if you want to traverse an edge, the weight of that edge depends on which direction you're traversing it, and also how long has passed when you're about to traverse it. So let me just give you an example so that it makes a bit more sense. So let's say we're at this node and moving to the 1. What does that mean? That means the 2 is in the trend setter component and the 1 is not. And the 1 needs to join the trend setter component, but the 2 is already in the component. What does that mean? Well, that means that the next time the trend setter changes to a 1, everything in the trend setter component will change to a 1, including this 2, right? And so this 1 will join the trend setter component because it will be adjacent to a value in the trend setter component and it will be equal to that value. So it must also be in the component. So if we're moving from node A to node B, then the next time we see the value of node B. So in this case, it was a 1. So the next 1 in the list of trendsetter changes is when that move will happen. So for example, in this case, where we're moving from the 2 to the 1, let's write out the time we reach A, and for each of those values, when we'll reach B. So if we reached the 2, and we're at moment 0, well then the time that we would reach the node 1 is 2 seconds in, right? Because that's the next moment when the trendsetter, and therefore the trendsetter's component, changes to the same value as the target node we want. So that's when that changes to a 1. So time 2. If we've arrived at the 2 at time 1, it's still time 2. The time that we arrive at the 1 is still time 2. That's because whether we arrive at this time or at this time doesn't change the next one after this. If we arrive at time 2, again it's time 2. So it's the next one on or after that moment. If we're at time 3 though, the next one after that is 4. So that's the 4. If we arrive at time 4, again it's 4, and if we arrive at time 5, then we will never change back to a 1. So this will never join the component. So this is never going to happen. We're never going to join the component. So if node A, we call this node A, if node A joins the trendsetter component on or before time 2, then node B will join at time 2. If node A doesn't join on or before time 2, well then if it joins on or before time 4, well then node B will join at time 4. This is node B. Otherwise, it will never join. So why have we chosen 2 and 4? Obviously because we have 1s in the trendsetter changes at these times. So in this case, the weight of this edge, right? In this case it was 2, in this case it was 1, in this case it was 0, in this case it was 1, in this case it was 0, and in this case, well, essentially in code we can use some really big number because this will never happen, right? It'll never join the component. So this edge has essentially an infinite weight, you could say. So that's the weight. So as we can see, the weight of the edge depends on when we arrive at the node from which we're traversing the edge, right? And Dijkstra's algorithm doesn't really support that, right? Dijkstra's algorithm is on a graph with fixed edge weights, but we can work with this. So first of all, what does the edge weight depend on? Two things, right? The direction that you're traversing the edge and the time that you arrived at that edge. So we can easily fix the direction issue. That's because, well, we can replace each undirected edge between each neighboring pair with 2 directed edges between them. So we can imagine 2 directed edges between each pair instead of 1 undirected edge. Let me just draw that. So we have these, and we have 2 directed edges between each pair. And we can traverse both ways. So we can imagine it like this, and now each edge no longer depends on the direction of traversal of the edge, the weight of each edge, because you can only traverse it in one direction. So the only thing that remains, this direction issue is fixed. the weight of an edge now only depends on the time of arrival, right? The weight of each edge depends on when you reached the point from which you're traversing the edge. So the weight of the edge depends on the time of arrival. So there are obviously some cases where Dijkstra's wouldn't work on such a graph, right? If the weight of the edge depends on the time of arrival, that might really mess things up. So let's say, well, for example, if we had a graph like this, where we were trying to find the shortest path from node 1 to node 4, and let's say the weights look something like this. So this is 5. Well, let's just say this is 1, this is 1, this is 1. And let's say this edge weight depends on when you arrive there, right? So if you arrive 1 second in, then the weight is 10. And if you arrive 2 seconds in, the weight is 1. Well, then it's obvious here that Dijkstra's won't work here, because what does Dijkstra's do? Dijkstra's works by greedily, essentially, choosing the node that's closest with the shortest distance to the source. So this is the source in this case. So it greedily chooses the node with the shortest distance to the source, and then it fixes that shortest distance, saying that that definitely cannot be improved. So it only considers the shortest distance through intermediary nodes when getting to later nodes. But in this case, that wouldn't work, right? Because it would fix the shortest distance to node 2 as 1, because the shortest distance to node 2 is 1, and the shortest distance to node 3 is also 1. But then when node 3 says, well, you can get to node 2 in time 2 by taking this edge of weight 1 and then this edge of weight 1, it would say, well, why would I do that? That's slower than just taking this edge and getting there in weight 1. But then what happens is this breaks down, because in this example, getting from node 2 to node 4 would be significantly faster if you arrived later. So if we had taken this path, which was initially slower because it got to node 2 later, well, then the weight of this last edge would have been 1. So our total weight would have been 2 plus 1, so 3. But what we did instead is we said, well, we want the shortest path, so let's take only the shortest path to node 2. But that means this edge ended up having a weight of 10. And so even though our initial path to 2 was shorter, our later path from 2 to 4 was longer. And so we got a longer total distance. So Dijkstra's will not work in this case, in a case like this. But so you might be thinking, if the weight of an edge depends on the time of arrival, then how do you run Dijkstra's? Well, in this case, it actually still works. Why? Well, we've modified the definitions of everything, basically, but the Dijkstra's algorithm still works here, because something like this counterexample that we drew that broke everything, that broke Dijkstra's algorithm, something like this won't happen in our problem. Well, what does something like this mean? So if the shortest path from, we had node 1, 2, and 4 here, but let's generalize that to A, B, and C. So A, C, and B. So if the shortest path from A to B goes through C, so shortest path from A to B goes through C, then that path will be composed of the shortest path from A to C, followed by the shortest path from B to C. That holds in our problem. I.e., in less formal terms, if you're going from A to B and you're going through C as an intermediary node, it's never beneficial to take a slower route from A to C, because it later pays off and gives you a faster overall route, because it speeds up this second half of your journey more than it slowed down the first half. So something like that can never happen in our problem. It's never optimal to take a slower route initially to an intermediary node because it later pays off. So why is that? Why does that hold in this problem? Well, if you take a look at this problem, the edge weights are kind of confusing here. So let's ignore the edge weights, but only think about the arrival times and the arrival times at one end of the edge, and then the arrival times at the other end of the edge, essentially. So the arrival time plus the weight. And we'll see that if you're moving from node A to node B, then the time you arrived at node A and the time you arrived at node B are related in a special way. So if you look at arrival time at B as a function of arrival time at A, that is a non-decreasing function. That's a non-decreasing function, which means that it's exactly what we said earlier. It's never beneficial to arrive at node A later because you could then traverse the edge and end up at node B earlier because it's a non-decreasing function. Why is this a non-decreasing function? Well, from the definition of whatever we have here. So the definition of if you arrive at node A at time t, if you arrive at A at time t, and you want to traverse the edge from A to B, well then, when will you arrive at node B? It'll be the next moment in time after t, or greater than or equal to t, such that the trendsetter changes to the value of b at that time. So if you arrive at node A at time t, and you want to traverse the edge from node A to node B, the time you'll arrive at B is the next time after t, so greater than or equal to t, when the trendsetter changes to the value of b. And so by definition, this is the next time that something happens after this current time, so that must be non-decreasing as you increase the arrival time at A. That means that if this is non-decreasing, again, this statement here holds that it's never beneficial to take a slower route. So Dijkstra's algorithm works, essentially. Something that might be helpful to imagine this is a similar problem where you have the same edge weight definition, essentially. Let's take the exact same layout of graph, something like this. And let's say that these are cities. These nodes are cities. It doesn't have to be the exact same layout. It could be any graph, but let's just draw it the same way. These nodes could be cities, and each edge represents, and again, we could do directed edges as before. And each edge represents let's say a bus. And that bus travels between those cities at fixed moments in time. So if you had a problem like that, where each edge is a bus between cities, and that bus travels, each edge has its sort of moments where that bus can move. So if you arrive at one city and you want to take this edge to another city, if you want to take this edge from city A to city B, then the time you'd arrive at B is simply the next time at which a bus travels from node A to node B. Let's assume the buses go between the cities instantaneously. The only limiting factor is when the bus actually travels. So if you're at node A, then, and you want to move to node B with this bus, then the time you'll arrive at node B is the next time after the time that you arrived at A, that a bus travels from node A to node B. It could be a problem like that. And that problem, if you wanted to find the shortest route from one node to another, that problem would have exactly the same solution. that you could use a Dijkstra shortest path algorithm to work out the shortest path between two nodes. Because even though the edge weight depends on the time at which you arrived at one end of that edge, Dijkstra's algorithm still works because it's never beneficial to arrive at a node later, because it leads to gains in time later on. So that's a similar problem that came to mind when I was explaining this, because so in this problem with cities and buses, this edge weight definition is a bit more natural, whereas what we're doing here in the spies problem is a bit more, slightly more artificial, slightly more forced in a way. So what we've been talking about this whole time means that we can run Dijkstra's algorithm on this. So we can start with the trendsetter only in the trendsetter component, so its distance is 0 because it's already in its own component. We can set up these edges. Well, we don't have to set it up. They're implied. The graph is implied. We don't have to actually build the graph. And so we run Dijkstra's algorithm on all these nodes. By the end of that, we will know the distance to each node. And what does distance mean again? The distance means the first moment in time when that node becomes part of the trendsetter's component. And so we run that, and back to what we're trying to find in the problem, that makes the rest easy, right, as we discussed, because we know when each node becomes part of the trendsetter's component, if it does at all, and the rest of the nodes don't become part of the trendsetter's component at all. And actually, we don't even need when each node becomes part of the component. We only need whether each node becomes part of the component. And so we take all the nodes that become part of the component and add on the number of nodes that don't become part of the component but initially already had the same value as the trendsetter's final value. So yeah, that's it. That's how my solution works. You run Dijkstra's algorithm with this modified definition of distance and modified edge weights, which depend on the time that you arrived at one end of the node of the edge. But Dijkstra still works, as we've seen. So you can run Dijkstra's, count how many nodes were reached, and then add on the number of nodes that were equal anyway. So that's the solution. Now I can take you through the code. So this is the code I submitted that got accepted during the contest. So, well, we've got input output in files because that's how the Olympiad works. That's the format it uses. Then input output optimizations. And then, so this part is the inputs. So as Boris' solution had, just like that, my S, which is the initial types of cutlery of every spy, I've put that in a one-dimensional vector rather than a 2 by something vector, because it just makes life easier, makes everything easier. So index 0 through n-1 of this will refer to the first row, and index n to 2n-1 will refer to the second row. That's S. Then A is what we had over here. A is this array in purple, this vector in purple, which is the values that the trendsetter changes to. So indexed from 1 to the total number of changes, and index 0 holds the initial value that the trendsetter has. So I input everything in S, and then I input every value of A from 1 to C, C being the total number of changes. And then I set A0 to S0, meaning I set the initial value that the trendsetter has to the value that the trendsetter has that we inputted. So I'll skip this thing for a moment, actually. I'll come back to it in a second. But so we want to run Dijkstra's algorithm here. So I have, well, this is a relatively standard Dijkstra's algorithm implementation. So I have 2n nodes. So I have the distance vector of size 2n. Initially, the distance to each one I've set as c plus 1, which is basically infinity, right? Because c is the number of changes, so the maximum distance that a node might have is c. If it joins the trend setter component right at the end on the last change, then its distance will be c. So I'm initially setting everything to c plus 1, saying that if it's higher than c, it doesn't matter what it is, I just know that it'll never join the trend setter component. So that's distance. Then we've got the priority queue sorted so that I get minimums instead of maximums. And so we start. Distance 0 is 0, so the distance to the source, the trend setter, is 0. And we put it into the priority queue. We have a scene vector as usual. I'll talk about this in a second as well. And so while we haven't found the distance to every node, we take the topmost one. We take, the priority queue, as usual, has pairs of time and node. So it's sorted by time. That's why that's the first in the pair. So we take the topmost one out of the priority queue, the one with the smallest time. If we've seen it, that means we've already fixed the shortest distance to that node, so we just continue. Otherwise, scene v equals true. And now what remains is to go through, I'll again skip this, to go through all its neighbors and try traversing those edges, right? So, well, I've got a vector called children here instead of neighbors, but it's the same thing. So if v is neither 0 nor n, then it has a neighbor to its left. So we'll add that to the children vector. If it's not at the end of the row, we'll add its neighbor to its right. If it's at the end of a row, then it doesn't have a neighbor to the right. And whatever it is, we'll add its neighbor opposite it to the vector of children as well. So now every node will have a children vector here when we've reached this point, which will have size either 2 or 3. So this node's children vector will go through every child in the children vector. And now we need to work out what edge weight this edge has, right? So we're moving between two nodes. So we want to find the first point in time from t when the trend setter changes to the value of this child, so to the value of node u. So how do we do that for each edge? Well, we could just do it iteratively, right, with brute force, which is what I initially did when I wrote this, just to test it out, but I forgot to delete this comment. But so you could do it with brute force, where every time you want to find something like this, you start at time t and just iterate forward in the array A, which is the trend setter changes array, and you just keep iterating until you find a value that's equal to VU, and then you stop, and that's the arrival time that you'll arrive at node U through that edge. So you could do that, but that would obviously be too slow, because in the worst case, you're doing one of those iterations every time you're trying to traverse an edge. So that's O of, well, what are the variable names? That's O of n times c, which is too big. So instead, the easiest way I found is not actually too hard. It uses the fact that we're running Dijkstra's algorithm here. So we don't ask for weights of edges in a random order. We ask for them in increasing order, in a non-decreasing order of arrival time. So we'll ask, what is the next 2 on or after this index? What is the next 1 on or after this index, perhaps? And then we'll move to the right and say, what is the next 1 on or after this index? So we will never go back in time, in a sense. So since Dijkstra's algorithm has this time t, it fixes them in a non-decreasing order. That means every next time we enter this loop, when we want to find the next point in time from t when the trend setter takes on some value, changes to some value, this t will be greater than or equal to the previous value of t that we checked the same things for. So every time that t changes, so every time we re-enter this while loop, the value of t will be greater than or equal to the previous value of t in the previous loop. Which means, if you look at the whiteboard, that we can do something like this, right? We don't need to binary search or anything. We could do it with a binary search, but using that fact that the value of t always is non-decreasing, so we always ask the next query on a value of t that's greater than or equal to the previous value. That means what we can do is actually store these in another structure, so we can store these by value. So let's say we have value, I'll use purple again. So in this case, we have 4 different types of cutlery. So for all of them, 1, 2, 3, 4, we will store the indices at which the trend setter changes to them. So for type 4, it's just index 0, so this one. For type 1, it's index 2 and index 4. For type 2, it's index 1 and index 3. For type 3, it's index 5. And so we've stored these indices. And so how will this work? So every time we pass a moment in time, we can strike the ones that are no longer relevant from the front of these lists. I'm going to take you through an example so it makes some more sense. So let's take this example. I've copied this over from down there, and this grid will store the distances to each node. So initially I'll leave them blank, but that means that the distances are c+1, so essentially infinity. So in the actual code I'd write 6 here, which is 5 plus 1. But I'll leave them blank for now. So the distance to the trend setter itself is obviously 0. And initially everything else is essentially infinite. So let's run Dijkstra's. So I'll indicate a black distance as a provisional distance and a red distance as a fixed distance. That will never change again. So in the scene Boolean vector, when we actually take a node from the priority queue and mark it as seen, I'll mark the distance to it as red, because that means it will never change after that. So we take this node, the trend setter itself, we mark it as seen. Now we need to traverse both of its edges. We say, let's traverse this edge. So if we want to reach this 2, when is the first time after time 0 that the trend setter changes to a 2? Well, we can just take a look at the value 2, take the first index at which that value happens, and that index is 1. So we can write 1 over here. We can also take this edge and say, what's the first time after time 0 when the trend setter changes to a 3? We can check the 3 vector here, and that's 5. So we write 5 here. Now, as we do in Dijkstra, we take the next node and fix it in red. So the next smallest distance one, and so that's 1 in this case. That's the one with distance 1, but it's node 2. the node with value 2. So we fix this, and we take each of its edges. Obviously, the edge upwards won't do anything because this is fixed, but the edge to the right will give us, so that we want the first moment in time after time 1 now, where we see a 1 on the board. And so now that we've changed the time after which we're asking, right, this red fixed time from which we're asking, so every query is of the form, what is the first time after this time when the transcessor changes to some value x? Every query is of that form. And because this time has now reached 1, it'll never go back down to 0. So every time we ask a question of the form, when is the next time after something that the transcessor changes its value to something, we will never be using that time after which we're asking will always be at least 1. So we can strike the 0 from the list here. So index 0 is irrelevant now. So we can strike it from the front of whichever list it's at. So now we fix the 1, and we want to take a look at this edge. So we're asking, when is the first time after time 1 when the transcessor changes to a 1 in this case? So that is value 1, first index, that's 2. So this is 2. And so again, because we've struck off of this index list, every value that is less than the current time which we're searching for, so we're searching for times greater or equal to this, since we've struck off every value that's less than that from the list, well then the smallest value in the list in the row that we're searching for will be the one that's the first value. That's the smallest time when that happens, because we've struck all the ones that are too small off of the list. So now when we fix the next node, so we will now fix this 2, because it's the next smallest. We'll now take a look at its edges, and we'll strike this 1 off the list, because we're no longer interested in times less than 2, so we'll strike the 1 off the list. And so now we'll try both the edges coming out of 2. Well, going backwards is not going to change anything. So going upwards, this edge, well, we want to know what's the next time after time 2 that we see a 3. And that is the first value in the 3 index list, and that's 5. Well, that's the same as we already had, so that won't change anything. But then this way, we're looking for a 2. So what's the first time that the transcessor changes to a 2 after time 2? So we check the 2 list, and that's 3. That's the first value in the list. So this is 3. Now, that's because that we struck off this 1, because we're not interested in index 1 anymore, because at index 1 we did have a 2, but that was before we reached this node. So that's how this works. So we can strike that off as well. So because we struck that off, we can just keep taking the first element in each list. And so that's constant time. So now we fix this node. And you can see where this is going. We strike the 2 off the list because we are no longer interested in times below 3. Then we try all edges from this fixed node 3 with distance 3. So upwards, that's the next 3 we see after time 3, so that's 5. And to the right, that's the next 1 we see after time 3, so that's 4, which is the first value in that list. Sorry, 4. So we've done that. Now we fix again the smallest value in here. That's this one, 4. We try all of its edges. So to the left is already fixed. Above, is another 3. So the first value after time 4, oh sorry, I forgot to cross this out. So the first value after time 4 is the first time after time 4 that we see a 3 is 5. So we get another 5 here. And then to the right, the first time after time 4 that we see the value 4, when is that? Well, we've crossed out the only time that the trend setter changes to a 4, so actually that's never. So we can write infinity here. But, I mean, we just leave it blank. But in the code, we'll have 6 written here, and 6 is essentially so big that it indicates that will never happen. So this will actually leave this as a 6. So why not? I'll write 6s in all of these. And 6s essentially mean infinitely large, because we'll never reach that point. And so we'll do the same. We'll fix this 5. It won't change anything for the rest. It'll leave this as a 5. And so we'll fix this 5 as well, and this 5 as well. And that's how it ends, right? Well, I'm not actually sure. The code might actually end up fixing this 6 as well, and trying to make some moves between those edges. Let's see where I'm breaking. But that doesn't really matter. Yeah, so as you can see at the end here, we will have, I forgot to strike this off as well. We'll have struck all of these off the list. And we will have the distance to every node. So I guess we can turn these red as well. But we will have the distance to every node in the list. So everything up to 5 will be reached, and everything that is 6 will not be reached. And so if we return to the code, this structure here, where I have every value by it, every index stored in a vector depending on its value in the trend setter changes array, in the array A, as I have called it here. That structure is called next occurrence. So that's a vector of vectors. And so as you can see here, I go through all the values in A, and I put them into the next occurrence array by their value. And so in a vector, actually, I did draw this on the whiteboard as removing from the front of each of these vectors. But in a vector in C++, it's actually really easy to remove from the back, but not so easy to remove from the front in terms of time complexity. So everything that I showed you here, I've just reversed it in the actual code. So I'll have these sorted in, stored in decreasing order. So that's why I iterate from the right side in decreasing order of index, because I'm pushing indices into this. So I'll have them stored in decreasing order. And so instead of accessing the front, I'll access and remove from the back. I could have also had these as stacks, by the way, because I'm just inserting and then removing. That would have worked as well. And so, well, we've already talked about this. And then last T is the lowest time that we still have that hasn't been removed from the last occurrence vector. So as we were working through this example here, as you remember, when we fixed the 3, for example, we want to cross out every index in this last occurrence structure that was less than 3. So for that, we need to know what's the smallest index that we haven't crossed out yet, so that we can start from there and work our way up until we get to 3. So that's last T. Initially, the smallest index that hasn't been crossed out yet is 0, because none of them have been crossed out. And so when we enter this while loop a new time, our queries will be what is the next moment after time t when we see a certain change in the trend setter changes. And so we want to remove everything less than t from next occurrence. So while last t is less than t, we remove that index from the back of whichever last next occurrence vector it'll be in, and we add 1 to last t. So this will bring last t and the next occurrence vector up to date, essentially, so that we can ask whatever queries we need. And so this, again, gets all the children, all the neighbors, and then for each neighbor, how do we calculate the weight of that edge? So if this is the initial value of the node that we're trying to get to, so that's the value of that node, and so the next occurrence of that after time t will be stored in next occurrence SU. And so if that's empty, that means there will be no more trend setter changes to the value we want. But if it's not empty, then we'll arrive at the other end of that edge at next occurrence SU back. So because we have these sorted in decreasing order, the last one is the smallest one. And so we take that. If it's empty, then we just take c plus 1, which is essentially infinity. And then standard Dijkstra stuff for this if here. So if next t is less than the distance to node u, then we update the distance to node u with next t, and we push this pair into the priority queue. So that's the Dijkstra's algorithm. And then at the end, we just go through every node and count the ones that we need to count. So we need to count which values by the end will have the same value as the trend setter. And so for each node, it will have the same value as the trend setter if it either was reached in the Dijkstra's, which means that it'll be in the trend setter's component at the end, or if its initial value is the trend setter's final value. So that's an alternative as well. So any node that satisfies at least one of those two constraints, for each one of those, we add 1 to the count, and we print the count at the end. So that's that. That's problem fork. That's my solution. I tried to go in depth there. I tried to provide some examples. And yeah, I mean, in general, this was the easiest problem, I'd say, from how many people solved each problem as far as I remember. I don't know the exact numbers or anything, but it felt like this was probably the easiest problem in the set, but it was still relatively challenging. There weren't any like giveaway problems in this year's final. So yeah, nice problem, and I didn't see the neatest way to solve it, but I'm happy I didn't, to be honest, because this was fun as well. So I'm hoping that you took something interesting out of this solution as well as Boris's neat solution. So that's all for problem fork. It was great that we could get Boris in for this session. So maybe we can do that for some of the future videos as well. Something like that should be fun. So yeah, this was enjoyable. I will catch you in the next video where things get exciting. So stay tuned, because the other problems were pretty fun as well. I'm currently in exam season, so I might not upload it for the next few days, but in the next few weeks, certainly, they'll start coming out. So there were
4 problems. This is the first one, as you probably know. Well, they aren't ordered in any specific way, but there are 4 problems. This is in my head, the first problem. So the other 3 are on their way. They have some interesting solutions. They also don't have unique solutions. There are a few solutions to most of them that I know off the top of my head. So yeah, stay tuned. Thanks for watching, and I'll see you in the next video. Goodbye.